Hello students, and welcome to section 6-1, Rational Exponents and Properties of Exponents. To kickstart our lesson today, we're going to be taking a look at example 1 by writing radicals using rational exponents. For part A, it says stamp A and stamp B have the same area, but their side lengths are expressed differently. How can you show that the square root of 2 is the same as 2 raised to the 1/2 power? As it turns out, these two quantities are technically the same, but it's again asking how can you show this. Alright, this is actually the first time that you've probably seen a number raised to a fractional exponent. You likely have seen the square root of 2 before, if not in my class necessarily, certainly prior to this in some cases. But the square root of 2 can be rewritten as 2 raised to the 1/2 power. Turns out there's a little number here. It's implied to be a 2, so it's the square root, or 2 here as the index they call it, and you can see it as the denominator of the fractional exponent. It's also implied here to have an exponent of 1 inside the square root, so it's 2 to the 1st power, and there's the numerator expressing really the same type of thing. So how do we do this? How do we show this? Well, we can go ahead and start the process. As it says, use the properties of exponents to show the following: that 2 to the 1/2 power, and we're going to go ahead and do the inverse here, or essentially the opposite operation, you can think of it as, by raising it to the 2nd power. If raising it to the 1/2 power is the same as square rooting, then squaring it will actually undo, so to speak, the square root process. And it's actually really nice to see here that if you square the 2 to the 1/2 power simply by multiplying 2 times 1/2, 2 times 1/2 is simply 1. So as you see here, 2 to the 1st power is what we call the radicand is in its original state, the radicand being the number just simply under the root. And that's what we're getting by quote-unquote undoing that operation. So 2 to the 1st here, just the number in the radical sign or inside of it, is what we're getting as a result. Then you can go ahead and notice as they prove out using the power of a power property. Power of a power property highlights that you can multiply exponents, just like I noted up above. And of course, also like I said, multiplying 1/2 times 2, you end up with 1. And therefore simplification yields this number 2, again the radicand as we say under the root. So as it turns out, the square root of 2 to the 1st, and as I indicated, here's your root, here's your exponent, is equivalent to 2 to the 1/2 power. Moving on, part B. Stamp C has different side lengths. How can you express the cube root of 5 squared using a rational exponent? Okay, so now we're going to go ahead and utilize similar aspects as it's denoting here, as remember the square root of 2 to the 1st being equivalent to 2 to the 1/2 power. So the cube root of 5 squared should be equivalent to 5 to the 2/3 power. Here is your index, or root if you prefer, same thing. The root is the denominator of your fractional exponent. While inside the radical, this radicand in its entirety, 5 to the 2nd, that of course is your numerator of your fractional exponent. So 5 to the 2/3 is the resulting expression. In general, rational exponents are another way to express radicals. If the nth root of A is a real number and m is an integer, then the following setup is true, such that A raised to the 1 over n power is equal to the nth root of A, and A to the m over n is equal to the nth root of A to the m power, or you could actually write it in parentheses. I actually prefer this final kind of setup here if you're going to compare it to this using this original fractional exponent, because as it turns out, quite a bit of questions are going to have a radicand that when you raise it to this m power requires additional math that may not necessarily be as easy to do if it's in this particular form versus this particular form. We'll see problems later that will justify this being probably the best form of all. Okay, so let's move on. Example 2. Use the product of powers property to solve equations with rational exponents. So what is the solution of 3 raised to the x over 2 times 3 raised to the x over 3 if it's equal to 3 to the 9th power? Okay, so there are some properties of exponents to take a look at yet again here on this. Most noteworthy here, when your bases are the same, there is something to be said about the exponents then easily being something you can add. Let's continue though and see how this process will unfold accordingly. So we're going to rewrite the left side of the equation with one exponent. So again, here's the original problem. Because you have the same bases of 3, you're able to combine the left side into one simple expression with one exponent. One base of 3 and one exponent. Now you are going to add x over 2 plus x over 3, which will take a little bit of extra work, of course, but that's a more simplified version. And this property is called the product of powers. Next, speaking of adding exponents, you can go ahead and see here they've got a common denominator of 6. So this first fraction, if you were to rewrite x over 2 with a denominator of 6, you can multiply it by 3 over 3. So 3x over 3 times 2, or 6, so 3x over 6. X over 3 getting a common denominator of 6, you can multiply it by 2 over 2, so 2x over 2 times 3, which again is 6. So now you've got two fractions as exponents, of course, that you're adding, and because you have a common denominator, you can combine as one fraction, adding 3x plus 2x. So let's see the next step unfold. So of course 3x plus 2x, as you see, is 5x. The denominator, of course, now is just a single number 6. And now you've got an equation of which you have, again, two bases that are identical. This is very, very good because, as it turns out, if the bases are the same on either side of an equation like this, you can easily just set the exponents equal to each other, which is exactly what they do in the next step. So if you take 5x over 6, set it equal to 9. Again, the bases are the same, so set the exponents equal, and we'll simply multiply both sides by 6/5, which is the reciprocal of 5/6, to quote-unquote undo the left side. So 5/6 times 6/5, 6/5 times 5/6 is in fact 1. So you'll have x on the left side, while 6/5 times 9 is 54/5. And that is, in fact, our final answer, the solution of 54/5. One thing that I encourage you all to do, really on many math problems as we've discussed in the past, and that is plugging in your answer into the original problem. If you were to plug in 54/5 in for x, it will bear out that 3 to the 9th power is the end result. So 3 to the 54/5 over 2 times 3 to the 54/5 over 3. Of course, multiplying those will end up being 3 to the 9th. Example 3. Use the power of a power property to solve the equations with rational exponents. What is the solution of 27 to the x minus 4 equals 3 to the 2x minus 6 power? So to start this process, we're going to go ahead and well, there's the original problem again. We're going to go ahead and rewrite the left side of the equation, if possible, such that it has the same base as the right side. So right now 27 and 3 obviously are not the same. So we have to consider all possibilities of which maybe rewriting 27 or 3 yields the same base. Okay, 3 I can't do a whole lot with at all, it's prime. However, 27 I can rewrite. I can rewrite it as 3 to the 3rd power, which is quite nice because, of course, look, the bases on either side of the equation are the same. Fantastic. So because these are the same, we have a left side with still this exponent to contend with. We're going to simply distribute actually in a minute. But that's going to be set equal, as you can see, to this. As we continue, like the last problem actually, check this out. So we've got 3 to the 3x minus 12, simply distributing 3 times the quantity x minus 4. So 3x minus 12. And on the right side, you simply, again, have just this exponent. This is great. We have bases that are the same and exponents that we can equate. Again, when the bases are the same on either side, we can set the exponents equal to each other. And that's exactly what we're going to see here. 3x minus 12 equals 2x minus 6. Do your algebra, which of course entails, they went ahead and subtracted 3x, and then they went ahead and, let's see, they added 6 to both sides to get negative 12 equals negative x minus 6. As you can see in the next step, they added 6 technically, and they went ahead and simplified. So negative 6 equals negative x, and then of course x is equal to 6 if you divide the negative from both sides. So the solution, of course, in this particular instance is 6. I again urge you to plug in 6 into the original problem. So 27 to the 6 minus 4 power. Does that equal 3 raised to the 2 times 6 minus 6 power? It should, but I would urge you to check that on your calculators later. Part B, what is the solution of 1 over 125 raised to the negative x over 2 equal to 1 over 25 raised to the negative x over 3 minus 2 power? A lot more interesting looking for sure because we've got fractions, but I want you to consider the possibility again of maybe us rewriting each base on either side of the equation such that they're identical to each other. All right, that should be one of the main goals anytime you see a problem of this nature. So let's see how we can manipulate. Step 1, rewrite the equation so both sides have the same base, like I said earlier. So now, as we can see what they've done, just simply rewriting the problem. So they're just rewriting, but in the next step, you can see what they've done is they've manipulated 1 over 125 as a base of 5 raised to a power that's negative. And I do ask that you check on your calculator that in fact 5 to the negative third is 1 over 125. As a matter of fact, if you just did 5 to the third, you'll find that that's 125. But if you make it negative 3 as opposed to positive, it actually takes the reciprocal. So it writes it, or you will see it on the calculator, which you can write later, of course, on paper as a fraction, 1 over 125. Similarly, on the right side of the equation, this base you can rewrite as 5 to the negative second. Okay, remember that, well, heck, if we just took 5 to the positive second power, that's just 25, right? 5 squared is 25, but because it's a negative 2 and not a positive, it actually takes the reciprocal again. So you need to write it and denote it, as the calculator does, as a fraction, 1 over 25. So 5 to the negative third raised to this power still from the beginning. 5 to the negative second raised to that power still from the beginning. Our bases are the same, actually, right? They're both 5 here. We do have a little bit more work to do, of course, with negative 3 and negative x over 2, but also negative 2 and negative x over 3 minus 2. But again, that's just a matter of setting them equal to each other, as they do in the, well, not exactly the next step, but this is just the next kind of simplification. So if you multiply negative 3 times negative x over 2, here you go, 3x over 2. Negative 2 times this quantity, make sure you put it in parentheses. So you're actually distributing, so to speak. So negative 2 times negative x over 3 is positive 2x over 3. And negative 2 times negative 2, of course, is positive 4. Okay, now this is great. Look at your bases again. The bases are the same, so you can set the exponents equal to each other. And because the exponents are simplified quite nicely, the rest of this should be smooth sailing. So let's take a look. Step 2. Okay, so as we can see, they've set 3x over 2 equal to 2x over 3 plus 4. They'll do a quick simplification, multiplying both sides by 6, which is smart because you have a common denominator, so to speak, here of 6. So multiplying both sides by 6, don't forget to distribute the 6 on the right side, will yield the following. 9x equals 4x plus 24. 6 halves is 3, 6 thirds is 2, so that's why you get those two respective quantities. Don't forget again, plus 24. Simply subtract 4x, and then of course divide by 5, and then in the end you end up with x equals 4.8. We will continue this synchronously, but I urge you also to take a look at some of those properties of exponents, which we will also be discussing together, just to kind of bring a lot of these ideas together as a class.